Okay, this video is about vectors and matrices. These are the things I hope to do in it. A little bit of explanation about vectors, the magnitude and direction, 2 or 3 dimensional. We use the Cartesian coordinates in Maya. We use what we call the right-hand system, which I will show you now in a moment. And today we're going to start with 2 vectors, vector A and vector B, and we can see the coordinates here. We're going to define those in Python. So let's take a look at Maya. Okay, this is the Cartesian plane. This is the x-axis. Here we can see positive numbers. There's negative numbers. This is the z-axis, positive, negative. And although we don't see it here, there's a y-axis which goes up, positive, negative. The icon in the corner here helps us to remember which one is which. We can see the different colours. And another way to remember it is to imagine pointing your right hand where your index finger representing the z-axis is pointing towards you. Your middle finger representing the x-axis is pointing to your right, and your thumb representing the y-axis pointing upwards. Now we have 2 vectors we're going to look at, as I said, A and B, and here they are. Here are the coordinates, so I've already run those on Python. We're going to add them together, and addition is commutative. We're going to add the first term of each. We're going to create a new vector called C, and to do that, we will add the first term of each vector together to get the first term in C. The second term of each vector added together will give us a second term in C, and the third term of each vector will give us a third term in C. And if we do that in Python, we will get 763 as our new vector. Another way to do it is to, let's say our point vector A starts at the origin, so does B. We can move B down here. So we're adding it, the tail of B to the head of A. Our new vector C starts at the origin and will end there, and that will be the same as we got 763. Now we can also subtract vectors, which is obviously not commutative, and it's the very same formula. This time it's D, it will be A minus B. This time of course we're subtracting it instead of adding, so back in here. Now same idea, but at this time our B will be a minus B, which means that while it is the same length, it goes in the opposite direction, and our new vector D again starts at the origin and comes back to the head of where the B vector, the minus B vector, is there. Okay, so next up now we are going to try and get the length or the magnitude of a vector. We use Pythagoras' theorem, which as we know is the square root of the various coordinates squared. In code, we're going to get the square root of the first term squared, A0 by A0, second term squared, third term squared. First of all, we import math, so let's just first of all actually maybe subtract. We've done that. Okay, we know that'll work, and then we're going to import math so that we know how to do the square root. Now there's the formula for the square root. There's this formula for the magnitude, and the answer of the magnitude is 4.358. Okay, so it's the magnitude of A. Now that we know that, we can find out where the unit vector is, and the unit vector goes in the same direction as A, but has a magnitude of 1. So we take our coordinates of A, A0, A1, A2 are the coordinates of A, or the X, Y, Z coordinates, and we divide each of them by the length of A. And that should give us the unit vector, and the unit vector, the coordinates are here. I have them already worked out, and you can see that they go in the same, the new vector goes the same direction as A, but it just has a length of 1 unit. Now after this we are going to start multiplying vectors, and there's 2 ways of doing that. The first one is called the dot product, and you can see the dot here, we're representing multiplication by a dot, and we are multiplying, it's very simple, the first term of each vector A and B, the second term of each vector A and B, the third term of each vector A and B, and we add those together. It's going to give us a scalar. And we can use this then, we have two formulae for the dot product, so when we get the scalar we can use it to figure out, by using the other formula we can figure out what the angle is between the 2 vectors, which will help us when we're working out our light calculations. And then we also have here we can work out the dot product by using that formula, and the dot should return what we call a scalar, a single number. So obviously we can't plot that here. Now the next thing we're going to do then is we are going to do the cross product, which is another way of multiplying two vectors, represented here by a cross. The answer this time will be a vector, and what we're doing is we're taking the first term of vector A, we're multiplying it by, the second term of vector A, we're multiplying it by the third term of vector B. We're also multiplying the third term of vector A by the second term of vector B, and we subtract that from that. All of this gives us the first term in our new vector, which we're going to call E. And similarly here, we need to multiply various terms from each vector, we'll subtract one from the other. Let's go back to Maya and we'll put in our code and run that, and then that should tell us our cross product is a new vector which we're calling E, and the coordinates are here. We can see that it's actually very, very far away. This is very useful because it is exactly at right angles to the plane. We can see if we line up the other two, we can see that it is at right angles to them, so it's very useful in backface detection, so in terms of what to render and what not to render. Now the next thing we're going to look at is matrices, and they're very, very useful in computer graphics because we can perform all of these functions by using them. Today I'm going to focus on the first three. This is what a matrix looks like. There should be number one there. This should be multiplying, so my apologies for that. Simply what we do is we take the top row here and we multiply it by this column. When we do, we get 3 times x, which is 3x, 0y, 0z, and 0. So x is going to map onto 3x. We take this line and we multiply it here. We get 3y, and we multiply this line here. We get 3z. So if we take the point 1, 1, 1, x, y, z, and we use this matrix, we should get 3, 3, 3. So let's have a little look at that. Here we have our point 1, 1, 1, and I am going to do things with a series of cubes which start at the origin and are 1 unit in each dimension. So the first thing we have here is a scaling matrix, whereby as we see 1, 1, 1 becomes 3, 3, 3, and indeed it does. If we scale it up, that's exactly what happens. Okay, we can see it there. That corner is now at the point 3, 3, 3. Similarly, if we have this dice here or this cube, and what we're going to do at this one is we're going to translate or move it. Where we had the 3's the last time, we have 1's because we're not going to change the size of it. We're multiplying x, will end up being multiplied by 1, it stays as x. 0 by y, 0y, 0z, 1 by 1 is 1. So our x becomes x plus 1. Y, multiplied by 1, add on 2, basically becomes y plus 2, and z becomes z plus 3. So our point 1, 1, 1 becomes 2, 3, 4. And we can see there that when we translate it using that matrix, sure enough, 2 in the x-axis, 4 in the z, and there's our 3 in the y-axis. Now the next thing we're going to do is we're going to do a reflection, again starting at the origin, and again I have my little point 1, 1, 1 there. We're going to reflect it in the xy plane, which is running along here, and when we reflect it we get a mirror image of the original. And the way we do that in terms of matrices is we simply multiply all our x coordinates by -1, so x becomes minus x, the y stays the same, the z stays the same, 1, 1, 1 becomes -1, 1, 1, as we can see it is here. Now other things that we can do, we can rotate, we all know what that is, not going to go into that in detail. And last of all, the last cube, I am going to use a matrix which will both translate and scale. So the 3's and these positions tell us that we're going to end up multiplying, for example, x by 3, add on 2, 3 by x is 3x, 0y, 0z, and 2 by 1 is 2. So x at 1 is going to become 5. Our y, which starts out at 1, will multiply by 3, but nothing added on, so that stays, that becomes 3. And our z, which starts out at 1, we will multiply by 3, and we will take away 1, so that becomes 2. So when we run that matrix on it, sure enough, we are going to get our point will be 5 in the x-axis. We can see here it's 5, it's 2 in the z, and it is 3 in the y-axis. And that is the end of my video. Thank you for watching.